Hello, everyone. Welcome to our next session. I hope you're all having a great week and had some time to review Halo 2 materials. There was a scope of our audit for variant 1 of Summa posted to announcement channel. You might want to have a look at it. Yeah, and without further ado, we can start diving into Summa Codebase with Enrico today. And Enrico, microphone is yours.
Okay, thank you, Igor, for the introduction. So, the subject of today's is the code overview. So we finally got into the code. Maybe, yeah. So this is like the Summa solvency repo, and you will always work within that repo. So everything is included there. We have okay, so let me first start with like a premise, maybe. So like we have like 2 overview session, but of course it's really difficult to go through each line of code in 2 hours. So my goal, like what I want to share with you, is like give you an understanding of the design of Summa. So like the why we made some decision, like where to find what you're looking for, and so this is like the goal is to give you like the tools to understand how the repo works and how it's made, rather than trying to get into every single piece of code. And I think this is also good because I don't want to influence you too much. Like I want you to have like a fresh mind to assess the security of the code rather than me telling you, okay, this is doing that. So I won't go like super deep into the code, but just give you a general overview to help you orientate yourself into our code base. So we have like three main folders, like the zk prover, which I think is where you will spend most of the time. So the zk prover contains, if you go into the source, you have like the main things are like the chips, the circuits. So these are kind of Halo 2 basically, and the Mercosum tree is a directory that contains the logic of the Mercosum tree. So this is, I mean, technically there's nothing zk in here, but we still put it inside the zk prover folder. And here you also have like the benchmarks and the examples. So we actually use this example more as a scripts to do something, but we'll get to that later. Then you have like the contracts folder that is it's basically a hard hat project that is like contains the source code of our contracts and all the testing for the contract. But you see that the contract is yeah, like 200 lines of code, but there's no any crazy logic. It's just like a contract for mostly like storage. So this should be simple. And the backend is there's no particular added functionality in the backend. It's just a way for, let's say, you're a custodian to interact with all the APIs to generate the proof. So if you remember, like there was this diagram, there were like some arrows starting from the custodian. Like in the backend, you have all the functionality to perform this whole flow. And as I mentioned before, I guess that this probably Summa solvency flow is the best example to understand how the whole thing work, and then you can, go and see, okay, this is coming from here. Then you can basically start from there and get deeper into the code base. So this is like the highest level as you can get, and while digging into the API, you will end up basically in the zk prover. So you will see that like the Summa backend is actually importing stuff from the Summa solvency package. So these are kind of 2 different crates technically in Rust, and the backend crate leverage the Summa solvency crate. So the Summa solvency crate is the one defined here inside the zk prover, while the backend crate is called Summa backend. So we'll start from the zk prover, maybe at in like half an hour, 25 minutes. I will stop and take questions and then continue. So as I think the first thing that you can start with is the Merkelson tree. So you should get familiar with like the structure of the Merkelson tree. There's nothing crazy honestly there, but I think it's a good starting point, or at least that's how we started. That's where we built first. The mst.rs is the entry point to build a circuit, sorry, to build the Merkelson tree. And this contains all the logic of the Merkelson tree. You can see that there's a tree trait. So the tree trait contains the core methods of the Merkelson tree. So as you can see, there are like some methods that are, we just have the signature inside the trait, and the struct, the Merkelson tree struct, will actually define what these methods do. While there are other methods that inside the trait, we already have like the logic implemented, so we don't have to specify it again when applying the trait to the Merkelson tree struct. And yeah, you can go over that and see how it works. Main thing is that we have like some ways to build this from a CSV file. So you just pass a CSV file and it gets parsed into a Merkelson tree, or from entries. So you basically skip the parsing part and you give values that are already parsed. And another important thing is that you see here generate proof and verify proof. And this is a Merkle proof. So this is not a zk proof, but as you probably understood, like our circuit is a zk Merkle proof. So the circuit takes this Merkle proof as an input and use that to construct the zero knowledge proof. And also something else that I want to point out in this Merkelson tree, that I realized that, yeah, we probably didn't name this properly. So when you see like the entry, for example, so each entry of the Merkelson tree is made by a username and a balance. We already saw that. But the username, so if we put like as a username Alice and as balance 10, if someone gets access to the proof, so the proof has the public input, the leaf hash, they can potentially brute force the leaf hash and read the balance of Alice. So this can be kind of, you can see the way of attacking the leaf hash and learning these inputs, like the pre-image of the hash. But this doesn't necessarily need to be a username. It can be like a username plus salt, or it can be the hash of the username plus salt. So this is not enforced by Summa, but you can do that. Like if you see like our CSV file, so in this CSV folder, we have some test vectors. Like you see that the username that we pass is not actually Alice or Bob, but they're like this random stuff that you can think of it as the result of like hashing the actual username and some salt that is then given to the user to perform the verification. So if you thought about this attack, that's probably legit, but I think it's yeah, we can mitigate this attack using some salt. So I will finish with the Merkelson tree. There's nothing really much to say. Just go through the code and understand it. because I want to spend more time on the ZK part today. So I think it will be both today and the next session on the ZK part. But yeah, let's start with the ZK part. So let's close everything that we don't need. So first of all, like as you probably saw from the scope, like this circum folder is not part of the audit. So this was just like an experiment with Nova that is the one that I shared you, like the presentation in ZK Summit London. But this is just an experiment, so it's not part of the audit. What is part of the audit is the Halo2 part, and this Mercosum3 RS file inside circuit is the core logic of our own circuit. So I listen again like the presentation that Nullity made last time, and think we're like completely in line in terms of like the syntax and the definition. So I'm happy about that. And yeah, let's go through that. First of all, we defined our circuit struct, that is this MST inclusion circuit, and we have some generic parameter attached to that. And this generic parameters, we set them as a generic as a way basically to enforce them to be known at key generation time, because these parameters are basically defining the skeleton of the circuit. So if you remember, like in Halo2, we have like these columns. So basically the number of levels, for example, will influence how many rows need to be used. The number of currencies and the number of bytes are also kind of influencing the structure of the circuit. And so this must be known at key generation time, because they kind of, yeah, I think I like to say that they define the skeleton of the circuit before we pass the witness, that is at proof generation time. So these are like the inputs of the circuit, but I mean, like this MST inclusion circuit is just a struct that we created our own. This is nothing like enforced by Halo2, and I will explain later what this means. We have this with instance trait that is just like an helper trait that allows us to access the values inside the instance column. So inside the instance column, we pass the values that are the public inputs, outputs of the circuit. And in our case, you will see that the public inputs are leaf hash, root hash, and root balances. So something else that probably I forgot to mention is that our Mercosum tree supports multiple currencies. So most of the time we saw like an example just with like one currency, but you can think that we can have many currencies there. So that's why the number of instances is a variable dependent on the number of currency, because we'll always have like one leaf hash and one root hash, but the number of balances inside the root is a function of the number of currencies. So that's why this is a variable. Okay, then we have like this circuit-based trait that is, yeah, there are like few methods that are defined to the circuit, but I don't want to make it difficult now, so don't worry about that. And yeah, and this is like the method to, this is important, like this is the method to initialize the circuit, or at least initialize the MST inclusion circuit struct. So we fill up this struct, we fill up all the fields of the struct, starting from a Merkle proof. So the logic, the process would be, first you build a Merkle sum tree using the CSV file. Then for the user you want to generate the ZK proof for, you first generate a Merkle proof, and then you use this Merkle proof as input to the circuit to generate the actual zero knowledge proof. So now we get into the core part of the circuit. As you probably saw working with Edo2, there are like, let's go here. So this is actually the only part here that is something that is required by Elo2. So you see that for our MST inclusion circuit, we are obliged, like we must implement this circuit trait. That is something that is coming from Elo2 proof. And this circuit trait contains 3 methods. So the 3 methods are like without witness, configure, and synthesize. So let's forget about this for now. The 2 main methods actually are like configure and synthesize. And the way I like to think about these 2 methods is like the configure function is basically the one that is called at the key generation time. So this is basically defining the skeleton of the circuit and the constraints of the circuit, namely like the relation between the different cells. And this there are, yeah, we can get later to the type of constraint, but in the configure function, as you saw, is like the for example, in the Fibonacci example, you were setting like this sum constraint that like 1 + 1 = 2, that like 2, well, like 1 + 2 = 3. So that's where you define the constraints. And in the synthesize function, you define the assignment. So this is called at proof generation time. And when you call synthesize, you will fill up this table made of rows and cells with your witness. So let's go through them then. The configure function is so this is the configure function inside the Merkle sum tree inclusion config, and the logic that we apply here is we create all the columns that we need. So there can be like advice column, fixed column, selector column, and we pass them downstream to our chip. So as you can see, what we are doing here is like, first we create the columns, and then we pass them to our chips. So we have like 3 chips: Poseidon chip, Merkle sum tree chip, and the rain check chip. And as you can see, I think this is a bit different from the example that Nality gave, because in that example, the columns themselves were created inside the chip. So why we are creating them inside the main circuit? Because we could have probably created all the columns inside the chip, but that wouldn't allow us to share the columns across different chips. So this is more like for efficiency reason. But as you can see, for example, like this advice column, like the third advice column inside this array. Each share is inside here, is inside here, inside here, and not inside here. So, well, basically, if you take like the first column of the advice, you will see that this is used inside all the chips. So that's why we create the column here and we pass them downstream to the chips. And also something else that I want you to notice is that in this configure function, we are not really writing any constraint at all. So what you saw, there was like the custom gates are not defined here, but they are defined inside the chip. So if we go, for example, here, we'll see that later more specifically, but the constraints are defined here. So in the configure function of the main circuit, we didn't write any constraint. So all the logic is actually inside the chips. But I want to tell it to you because you can, like, the existence of the chip is something that is not like Halo 2 doesn't know about the existence of a chip. Like a chip is something that we just create our own, and inside the chip there's no trait that is enforced by Halo 2. So in theory we can, I don't know, like we can call it whatever. Like chip is how do you say, like a social construct. Like it's not something that is required by Halo 2 as an API. And we could potentially just write all our constraints inside the configure function and all our assignment inside synthesize without having to have any chip, and this will be fine. Like the important thing is what Halo 2 wants from our circuit is to have these free methods. If we use chips, it's probably for convenience, for like encapsulation of logic, for helping ourselves to test out smaller components of the circuit, but the chips themselves do not need to exist for what Halo 2 wants, basically. So this was like the configure function, and then there's the synthesize function. So again, if you see here, we build the chips, and then all the assignment function to the table is done using methods on the chip. So for example, this hash, then there's like for example, rain check chip assign. So this is the one to perform the rain check. Then there's like some where are like the sum. So this is swap hashes from per level. This is also another assignment function on the chip. We're gonna see them later. Sum balances per level. This is also an assignment function defined on the chip. And last thing that I want to tell you about this is that there are actually a few methods that are defined on the circuit that are free, basically. And these are the ones defined in this trait: the expose public method, the assign value to witness, and the load method. And these are defined on the circuit when we implement this trait on the circuit, while all the logic, the remaining logic of the assignment is defined inside the chips. And like if you remember the last time that I presented you the structure of the circuit in pseudocode, like how I did this was basically on one side I had this synthesize function, And on the other side, I was like drawing with my iPad. So if you can, if you print this, or you don't need to print it, but if you follow what I did in the previous session with this synthesize function, I think this will be helpful for you to understand how everything works inside the circuit. So what I suggest you is to start with this file without necessarily going through the chips yet. You can go through the chip later, but this helps you understand the logic of the circuit. Okay, what I want to say here. Okay, let's go into question now, because maybe you probably have question, and maybe your question will help me. I don't know, if I miss something here, I will come to my mind. See, chat is empty. Oh no, it's not empty. Okay, do you guys have any question?
I have a question. Do you have docs for Rust crates online somewhere, or they're not posted?
Yeah, I think you need to run it yourself. So if you
Okay.
do this, then you have this. So it's not deployed, but you can run it locally.
Yeah, I see also Ali's having a question.
Yeah. So Enrico, this is higher level question, just trying to maybe tie the implementation with some of the theory that we talked about yesterday that Noel he talked about regarding Halo 2 versus R1CS. So you were talking about instances and that how that is dependent on the number of currencies. So which means you can instantiate a different instance depending on the number of currencies. So my question is, this is maybe potentially one way we can see how Halo 2 is advantageous over R1CS is that if we were using R1CS and Gross16, with each one of these instances, we would need a different setup for a new circuit. While here, we are instantiating different instances, but we are not changing the setup. Is that understanding correct?
Okay, yes. So thank you for the question, because it made me also remind something that I wanted to share with you. So when I say instance, I don't mean the instance of the circuit, but I mean the instance column. So as you probably remember from the lecture that Nullity gave, in Halo 2, we have three types of columns. So there are like advice column, there are like fixed column, and instance column. So the advice column are filled up with the witness at the proof generation time. The fixed column are defined at key generation time, and the instance columns, which in our case is just one column, this one is filled with the public inputs, and this is filled with public inputs at proof generation time. So the way it works, and you will see this in the tests, for example, is okay, no, this is wrong. So when you see here, like what we do when we generate the proof, we also filled up the public inputs with the instances. So the instances are as you know, as I said before, like the root hash, leaf hash, and root balance. And what we are doing inside the circuit is we are called expose public. So what this expose public function does is, if you see from the comment, enforce copy constraint check between input cell and instance column at row passed as input. So for example, here we are saying that the current hash that is computed inside the circuit must be equal, so this is what the copy constraint means, to the row 0 inside our instance column. So you see column instance. So this basically is a same way of like exposing this to public. So that's why the expose public name. So this is not technically what probably Ali intended as a notion of instance is a different one. But what you said, Ali, is still very relevant, because I mean, your example is also correct. Like for different, let's say, for every combination of these parameters, we need a different circuit. So we need a different setup. And if we were using R1CS and Groth16, it would be like a huge burden for us, because we will need to do a setup. I don't know how many combinations probably there are, but I don't know. Yeah, like many combinations. And that would be like, for DevOps, probably impossible to do, but we are lucky that using this Plonk prover, we don't need to run a customized setup. And running a customized setup is very painful. Like you need to call people, you need to organize. So yeah, that's also correct what Ali said. And something that I just touched briefly is this prints folder. But I think, so for me, when I started, was the best thing ever for like debugging. I mean, the best thing that at least ILO2 gives us. And so I think you should really get familiar with this, because it's really helpful. Like this is a print of the structure of the circuit, and what you see is that this kind of rectangles in black are the region. So this is like the name that we assign to the region, and each smaller, let's say, for example, each smaller rectangle is a cell in the circuit, and you see there are like two different type of green. This kind of darker green means that there's some constraint applied to this cell, while the light green means that there's no constraint applied to that. So I remember Nality also mentioned, like, how can you check if a cell didn't make to a constraint? That's a good way, and it probably indicates that there's a bug. Well, I'm not saying that this is a bug. I think this is expected, but this is a way to check if there are bugs in the circuit. And yeah, this is like a perfect way to make sense of the layout of the circuit without getting into the deep of ILO2 API that might be intimidating at first. So I think the technique that I probably suggest you is first understand what is like the structure of the table, what is like the logic of the circuit, what are like the constraints that we apply, and then you can check if the API are doing what we expect them to do. So that should be probably a good logical process. And again, here, like the columns in pinks are the advice columns. So I think we only have free advice column because we want to save space, basically make a short proof. And all this in blue are the fixed columns. And I think that the first, I think that these ones are like the selectors. So the one with like this light purple, I don't know if it's a purple, but this light purple are like selectors. And this is telling you where selectors are activated. While this part is the fixed columns. So for example, you see that this is called like load range check table of 8 bits. So this is a region where we fill a table with values in the range of 8 bits, and we're gonna use that for range check. But yeah, I think this is really useful for debugging, and we have also, I mean, this honest like this one and this one should be deleted because these are no longer relevant. But the range check actually is the printing of a chip. So that's what I also meant, that you can test chips individually. Okay, I spoke a lot. I don't know if there are other questions.
No, not at the moment.
Okay, perfect. So the other things that I want, hey, how can we have different colors in a column? Is like why we have, I guess the question is why we have different columns in a column. So there's a meaning behind that. As I said here, like the green and light green means like if a cell inside a region is part of the constraint or not. And so this is why you have like these two different colors. And here, honestly, I don't know why this is color. I think this is probably telling that there's a selector being activated, but I'm not sure. Because it always appears here. Yeah, I don't know, honestly. This will be interesting to see why there's like this color inside this cell. There's also here. Okay, let me write it down. I will try to figure out what's that color. Is there a mapping available somewhere of colors? I don't know. I learned it from the T-Rex Park Halo 2 tutorial, so that's where they were explaining it. Do you use this layout using this? Yes, I think so. We basically wrote the script to generate the layout in the test. So is this test the one that you use for printing? So this is what Igor mentioned, and you can run it like this command also activates this feature. That is one that activates the printing. Okay. What I want to do now is go through the logic of the Mercosur tree chip and leave the other two chips for the next session. First of all, let's compare the three chips, because you see that there's like some common structure there. As we said, we have like three chips: Mercosur tree, range check, and Ash and Poseidon chip. And they all have the same methods that are also the one that Naliti described last time. So construct, then we have like the configure method, that is the one defining the constraints. And then you have, let's say, a class of methods that we can define assignment methods that are the one where you define like how to fill up a region. So this is like the Merkelson tree chip. I will zoom out a second because I just want to show you like the structure. So construct, then configure, then here there's like assign. And also inside the hash chip, you see that there's construct, configure, and hash. And like the Poseidon chip is actually using another downstream chip that is coming from Halo2 gadgets. So we don't have written our own logic to perform the Poseidon hash. We just we needed to create our own chip because of the columns. So we wanted to pass some columns from upstream, so from the main circuit. So that's why we created this. It's like a wrapper chip, really, that allows us to interact with this POW5 chip from Halo2 Gadget. So I don't know if this is audited. I think so, because this is like I guess this is coming from the original Zcash branch. But it will be, I mean, you can also check if this was audited or not, but I think so. So today we're gonna start with the Merkelson tree chip. So this Merkelson tree chip contains the logic of some operations that are performed inside the Merkelson tree. And these are mainly, these are like two very simple logic, but I think it's a good way for you to start understanding the design of these chips. So the first logic is the swap hashes per level. As we said in the previous session, the order of the input of an hasher function influences the output. And when we hash like two nodes, we need to know which one is on the left and which one is on the right. And if you remember, we use this bit vector that is called path indices to tell if it's one, it means that we are like the element of the Merkle proof is on the left. And if this index is 0, it means that it's on the right. So there's no swapping needed. And this function, yeah.
Enrico, can I zoom a bit, please?
Oh yeah, sorry. So this is the swap hashing, but I wasn't referring specifically to the code. I will get into the code later. And the second function, the second rule that we define inside the chip is just the summation of the balances, really. So this is really simple. But so again, going back to our mental model, they're like the configure function is the one that defines the constraint. Especially what we define here is a type of constraint that we can call a polynomial constraint or custom gate. And there are like 3 custom gates that we write here. So first of all, there's like a bool constraint, because we need to enforce that this index in the bit vector is either 1 or 0. So we don't want it to be 2. If it's 2, there might be some unwanted consequence. So we need to enforce that this is 2. And what we do here is just like writing a constraint that is activated by this selector. So by this bool and swap selector. And the constraint takes a cell at the column C. at the current rotation. So this means that when the selector is activated, the cell that is queried is at the same row as the one when the selector is activated, and this is a polynomial that is basically enforcing that this has to be either 0 or 1. So this is something that you should check if this is like sound or not. But this is the logic of the constraint, and here we are like just creating the constraint. Later on, we're gonna tell when to activate the constraint. Okay, I hope this is clear because it's very important. Like now we are defining a constraint that potentially could be like applied to every row, every vertical shift in our table. But we don't want it because if you go back to the printing, like this will be like the third the cell in the column C. We don't want this to be either a 0 or 1 every time. We want it to be a 0, 1 only here when we say assign node hashes per merkle-tree level. So this will be actually the cell that contains the swap bit, and this is where we need to activate this selector such that this Boolean constraint is activated. Okay. Oh, I lost it. The second constraint that we apply here is the swap constraint. So the swap constraint is making sure that the swapping is performed correctly according to the swap bit. So again, going back to the printing, this is again in the same area. Like when you do like this assign node hashes per merkle-tree level, this we have like this region is made of six cells, and the second row contains the first two cells of the second row are like the swapped hashes, and this is like the logic of this. So like the swap bit is at the column C. At the first row, we have the left and right that are not swapped, and on the second row, so you see like we use rotation next. At the second row, at column A and column B, you are supposed to have the swapped value. So when you activate this selector, that is the same as before, every time you activate this selector, this will check that at the current row, the cell in the column C is a Boolean. And it will also check that like the element in the column A and the element in the column B at the next row, next relative to when the selector is activated, are equal to the swap of column A and column B at the cells at column A and column B at the current rotation according to what the swap bit said. So, and this is like the logic of the constraint. Again, this is a polynomial constraint. And the last constraint is the sum constraint. And let me go back to this thing. When this is activated in this region, some nodes balances per currency. We're gonna see later where this tag come from. This is defined in the assignment function, and when we sum, we basically assign the balances, and then we perform the sum. So this is like the simplest custom gate that you will see probably, and this is just taking like the cell at column A at the current rotation, the cell at column B at the current rotation, the cell at column C at the current rotation, activating and basically querying the selector. And when the selector is activated, is enforcing this constraint. So like you can think in an abstract way that by default, Elo2 is enforcing this constraint at every vertical shift. So in theory, at every row, these three cells at every row, you have this some constraint applied. But because we don't want it to be activated at every row, we use this selector, and by default this selector is set to 0. So even if like in another, like let's say in this first row, even if this constraint doesn't hold, well, the constraint will technically hold because the selector will be equal to 0. So this expression will be like 0 times something and will be equal to 0. So the constraint is met. But when we want actually to enforce this constraint, we will activate the selector. The selector will go to 1, and then this expression will be 1 times left plus right minus computed sum. And this will go to 0. So namely, like the constraint will be satisfied only if this expression goes to 0. So that's how you should think about selectors. I see that we don't have much time, but okay, maybe we can stop and start from here the next time. But I really, really encourage you to go through this assignment function by yourself, because they are kind of complementary to the constraints. So in this function, we are gonna assign the values. So whenever I call this swap hashes per level, I'm gonna fill the table with like this current hash and perform the swapping. And I will tell, okay, since I'm performing this assignment, this selector, the Boolean swap selector, is enabled. So when we enable the selector, we are basically gonna enforce the constraint that we defined before. So the process is you write the constraint. So this constraint is kind of encoded into the skeleton of the circuit. Then you fill up your table with the witness value. And when you want to activate the constraint, you enable the corresponding selector. And when the selector is enabled, this will perform the check that you define inside of this gate. Okay.
Yeah, thank you. Great explanation. Thank you, Enrico.
Okay, is there any question? Otherwise, I can say a few things more, but I will prefer if you have questions. Okay.
There are no questions. I think you can.
Okay. So I will take this last 4 minutes to explain you what are like the type of constraint that you can set in Elo2. So what we did up to now is just like this is like one type of constraint. There are these custom gates, and these are defined in the configure function. So if you remember before, I said that the configure function that, so for example, like this configure function is actually called in the main circuit. Here, when we say like Mercosum tree config, so this is when this configure function is actually, the configure function of the chip is called in the main circuit. But I said that the configure function is the one that is like defining the constraints and defining all the skeleton of the circuit, while the synthesize function is just for proof generation and for filling up the table with the witness. This is not completely true, and this is something that was kind of confusing to me at the beginning, but there's also another type of constraint that is defined in the assignment function, and this is the copy constraint. So copy constraint means that you're like taking a cell and you're copying it inside another cell in your table. So for example, we are applying this here. So we are just taking this current hash that is one cell that was already assigned, and we are copying it inside this other region. So this is the second type of constraint. And even if this constraint is defined in the assignment function, this is still part of the key generation phase. So when you run your like the ceremony, and when you run the key generation for the prover and the verifier, these constraints are also part of this key. So they are also part of the skeleton of the circuit, so to say. And the third type of constraint that we have, that Elo2 has, is the lookup constraint. We're gonna see that in the next session when we are speaking about the range check, but you can see this here. And the good thing about the lookup constraint is that this is also defined inside the configure function. So these are the three types of constraints that Elo2 uses. And another thing that is important to note is that also this is something that led me to some bugs at the beginning. Well, you don't need to write circuits, so probably it won't happen to you. But just to know is that you cannot write constraints between two different regions. So the constraints can only be activated inside the same region. So if let's say I enable this Boolean swap selector here, and let's say that in the bool constraint, I'm querying something from the previous. So let's say this was like prev. If I'm querying stuff from the previous row, and this is activated at the offset zero inside this region, this won't be able to kind of query the cell inside another region. So that's just because how Elo2 is designed. So the constraints must be like self-contained inside the same region. So this is very important. Copy, okay. Copy constraint, lookup constraint, and custom gate or polynomial constraint. Would you explain again the meaning of enable a selector? Yes, absolutely. So the selector is probably the, so I don't remember what was the line. Okay, so the selector is very, very important because the constraints are activated and applied relatively to a selector. So let's see the logic here. First of all, we pass the region in this lambda function. So the region is like a portion of the table. Okay. So we enable the selector at the offset 0 of the region. So it means that at row 0 inside this region, the selector is enabled. So when you enable the selector, let's remember the name of this selector is the Boolean swap selector. Automatically, the Boolean swap selector will go to 1. So this constraint will be, this expression will be equal to 1 times swap bit, blah, blah, blah. And since this expression must be equal to 0 at every vertical offset, by default, the selector is set to 0. So this will be always equal to 0. But if we set the selector to 1, the expression to be equal to 0 must be of the form s times this must be equal to 0, or this must be equal to 0. So when you activate the selector, then like the following logical step is that you will query the cells in relatively to the selector. So in that case, this was the one that I just changed. The cell that would be queried will be the one at column C at the same offset, in this case, when the selector was activated. So that is like the meaning of the offset of the selector. And in this case, we use the same selector for 2 constraints because these 2 constraints are always enforced the same place. So we kind of save some space by using a selector twice for 2 different constraints. Does it make sense to call the third one row constraint? Okay, maybe a better name would be call it like a table constraint, or advice table constraint, because what we are doing here is we're like telling that there's like some relation need to be enforced between some cells in the advice column. And this is also something that going a bit back into the theory, like a difference from R1CS and Groth16. So when you write a constraint in Groth16, you can only, they must be in the form A plus B. So you can do many addition, so A plus B plus C plus D, etc., times D. So you can only do one multiplication. But in this custom gates that's why they are called custom, you can write any operation that you want. So you can say like A times B times C times D times E, where like A, B, and C, D, E are like cells in the advice column. So this is also an advantage of AO2, but this comes with a cost. So if you create like gates, so this kind of type of constraint with many multiplication, the resulting polynomial will be at I degree, a polynomial of I degree, and this will be expensive. So for performance reason, it is not advised to create constraint with like many multiplication inside, even though you can do that as opposite to Groth16, where you're basically bounded in the way you can write this constraint. And that's why when you see in Circom, there are like these crazy loops for like writing just a logic of something that is probably simple to write.
All right.
Yeah.
I think that's it for today. Thank you, Enrico, very much. It was a very good intro into the code base. So yeah, thank you, everyone. We're gonna see you again on Monday for another, I think, code base intro session, right?
Yes, yes. So I think Monday will be continuation of the zk prover, and I think Wednesday, when is the next one, will be contract. Wednesday or Friday, I guess.
Sounds great. Right. Thank you. Have a good day. See
Okay,
you in
thank you.
Discord.
See you.
Bye bye.
Bye.